Hey guys, welcome to Chapter 10 of our pre-calc, statistics and probability. We're gonna break this one up into two parts because they really packed a lot of content into one section here. And so we're gonna get part one done in this lesson, and then we'll get a follow-up lesson for part two of this. So a lot of probability stuff that we'll be going through in this first section. A lot of diagrams. Definitely something to focus on is making use of these diagrams in order to help with our probability scenarios. So let me get moving into this. So we're going to start with very basic ideas of probability here, which is taking a look at the number of outcomes for basically ways of getting what you want, right? Number of outcomes in a certain event out of the total possible. And so the total possible is always our denominator. Best phrase for that is called the sample space. So keep in mind, you're going to hear this one come up quite a bit. Sample space always represents your total possible items to choose from. So that's kind of a key one in this. So one of the things that we're going to look at is using a sample space. Let me zoom in on this a little so you can see it nice and clear. Is using a sample space to help set up your probability scenario. So obviously, if we were looking at just tossing two coins and wanted to look at the probabilities of that, well, one easy way of dealing with something like two coins is just to lay out the sample space, lay out the total possible items that could happen if I toss two coins. And so here's the four outcomes that could happen. Could both be tails. Maybe the first one's tails, second one is heads, or vice versa, or they're both heads, right? So there's four ways you could toss two coins. That's our sample space. Guys, do keep in mind the order is important on this, and so tails heads is different than heads tails because it's affected by which coin it came from, and so it does create different outcomes if you switch the order, and so that does matter. But now if we said, okay, what's the possibility of getting two heads? Well, you can see one out of those four cases fits that scenario. There can be tougher questions though. What if they said, what's the probability of getting at least one heads? Right, well, now I can look at that sample space and easily say, well, 3 out of the 4 cases have at least one heads in it. Okay, and so by laying out the sample space, it really helps answer a lot of the questions. Some, of course, you really don't need to list out things like that. If you look at the second one, if we're talking about a deck of cards, obviously you're not going to list out what's all in a deck of cards, right? That would take you all day to answer a simple question. So some of these we just need to be familiar with the sample space, but we wouldn't actually write it out, right? I understand the sample space of the 52 cards that are in a deck. I know that there are 4 queens in a deck of cards. So the chance of me pulling out a queen from that deck of cards would just be 4 out of 52, or you could reduce that to 1/13. What have we talked about? Rolling 2 dice. When it comes to rolling 2 dice, there's a great diagram for rolling 2 dice that we call a lattice diagram. Very simple. If I was to look at 2 dice, obviously one die has 6 items on it and the other die has 6 items on it. So we're basically creating for ourselves a 6 by 6 grid that lays out all the possible outcomes of 2 dice. And if you just think about it logically for a second, if I was going to create a 6 by 6 grid, how many possibilities is that? All right, it's got to be 36 possibilities. So right off the bat, looking at the lattice diagram, I know that the sample space contains 36 items. So what have we talked about rolling a sum of 4? So what some people I'll see do is they'll try to list out the outcomes like this, and they'll say, let's see, I could get a 1 and then a 3, or a 3 and then a 1, or a 2 and a 2, and they really try to go through all the possible outcomes. It's easy if you do it this way to overlook something, and so using a lattice diagram, I would say, is the best approach for this. So let me show you that real quick. It's on the next page. It looks like this. So this is what the lattice diagram looks like. Now, let me just tell you, if I was answering a basic question on tossing 2 dice, obviously I'm not going to fill out all this information because that would take me all day, right? I would do a very skeleton outline of this where I would literally list 1 through 6 across here, 1 through 6 vertically, and that's it. That's all I would list. Because from there, then I can go through and basically check off the areas that fit the description that they're talking about. So when they say probability that I get a sum of 4, well, I would check off the 3, 1, this area right here where I see 2, 2, and then obviously 1, 3. And I would just put little checks right there. Check, check, check. And then I'd say, okay, well, it's 3 out of 36. And that's the best approach to using this lattice diagram. This is great to look at because it does at least show you all the possible combinations. But typically you wouldn't have this in front of you, and you'd have to make your own diagram. So we would quickly sketch out a 6x6 outline without filling out all the information. This one's kind of neat because they actually, where this one shows you each die individually, this one shows you the sum of the 2 dice put together. Sums work diagonally in this diagram, so they're really easy to identify. Obviously, here's our 3s, here's our sum of 4 that we just identified. Right, you got your sums of 5. Right down the heart of this, you get the 7s. There's more ways to get a 7 than any other sum with 2 dice. That's why, if you were to look into the game of craps where you're tossing 2 dice, 7 is craps because there's more ways in the house's eyes. They want that. That's a good thing for them because there's more ways to get a 7 than anything else. So they sort of build up to the 7s and then work themselves back down as you keep going that direction. So that's what a lattice diagram looks like. We'll talk more about that in just a second. The last one they mentioned is just more of that sort of word problem case. So you got tendinitis. Doctor tells you that further tests are needed. Yada, yada, yada. And then they talk about the causes that we're looking at here. Right? So what they're wanting to point out in this is when you deal with probability, the cases have to be equally likely in order for you to just look at this sample space and say what the probability is. When we talked about, let's just say these 4 outcomes, well, these 4 outcomes are equally likely, right? That's 1 out of 4, 1 out of 4, 1 out of 4, 1 out of 4, right? They're all equally likely. But when you talk about something like this, these are not necessarily equally likely, right? All these different diagnoses that you see on this, there's a weight to them. Some could be more likely than others, and so it's not as easy as just saying, well, it's like a 1 out of 4 chance. And so that's what they were just trying to point out on this, is if your events are not equally likely and you don't know how they're weighted, then we could not actually determine a probability from that. And they talk a little more about that in the paragraph down below, so you're welcome to take a look at that on your own. So on this page, I just had the lattice diagram for you. Down here in the next slide, they laid those out in terms of probabilities. But like I said, this is nice to have if you have it. But there's a good chance that you're going to run into a test or whatever where you're not allowed to have notes in front of you. And so you'd want to be able to do a quick sketch of an outline like we talked about right here. You go to the next one. So let me give you an example of how I would approach something like this. So if we had said, let's find the probability of a sum that's divisible by 4 with 2 dice, right? And so if this is what I had, yeah, great if you already had the lattice diagram drawn out like they did, but like I said, typically you're not going to have that. So what I would just do is, here's one die, here's my other, right? And so I would just look at that simple skeleton outline and just say, where are my sums divisible by 4? Obviously, the largest sum of 2 dice would be 12, right? This is the largest sum. So if I think about my multiples of 4, right, obviously 4, 8, and 12 are going to be the sums divisible by 4. So if we just look for our sums of 4, 8, and 12, so remember these were the sums of 4 in this diagonal. My sums of 8 would start down here where I see the 6, 2. So 6, 2, 5, 3, 4, 4, 3, 5, and 2, 6. So there's our sums of 8. And then sums of 12, there's only one way to do that. That's your 6 and 6. And so now I can simply look at those x's and say, well, how many x's do I have? There's 9 of them. I know it's out of 36, so right off the bat, I'm seeing 9 out of 36, which we obviously could reduce. So this is the way I would use a lattice diagram. Obviously not filling out the entire middle, just going through and checking off the winners. It's kind of your best approach on that. They do mention just kind of the basics of a probability function. Something you guys really already know is the probability of an event has to be between 0 and 1 in terms of decimals. In terms of a percent, we would say it has to be between 0% and 100%. Right, and so that's basics. I think you guys already know that. Let's move on. Just as a kind of a quick note here, and again, this is real basic, but let's just think logically on something like this. They want to make sure that probabilities are reasonable, right, and that this is something that could actually exist. So if you were talking about this Final Four basketball tournament, and they're talking about strengths and weaknesses of the 4 remaining teams, and they said, okay, here's our probability distribution. The first team has a 2 out of 5 chance of winning. Second team has a 1 out of 3 chance of winning, on and on, right? And so they have identified these probabilities for the 4 teams. Well, if you look at that logically, is that realistic? One of those 4 teams has to be the winner, right? Which means this does represent the entire sample space, which means the probabilities in a sample space have to add to 1 in order for that to be true. And so what they're saying is let's test those. If you add all 4 together, do they add up to 1? And if they don't, like those don't, then that's not a reasonable probability function, right? That's not valid, right? So whenever you look at a sample space, all of your outcomes should add to 100% in order for it to be a realistic scenario. All right, let's talk about some specific problems here. So Dylan opens a box of a dozen chocolate creams, offers 3 of them to Russell. Russell likes vanilla creams the best. All chocolates look alike on the outside. So 5 of the 12 are vanilla. What's the probability that he picks vanilla? So let me give you 2 ways that you could address some cases like this. And this is where we're going to start getting into just approaches to different kinds of problems. So let's just look at this at purely laying this out step by step. And to be honest, this is actually one of my favorite methods of doing probabilities is just list out the options. Just go down the list one by one and think basic, right? So if I'm Russell, so you got these 12 donuts, only 5 are vanilla. So we want to know that if he picks 3 of these, that they're all 3 going to be vanilla. Okay, well, let's just go down the list for a minute. If he reaches in and grabs a donut, what's the probability that the first one that he picks is vanilla? 5 out of 12, right? So he's going to reach in, and 5 out of 12, first one's vanilla. In order for this to work, all 3 of them have to be vanilla. So if he reaches in again, in order for this outcome to happen, right, we're under the assumption that the first one that he picked was vanilla. So then what's the probability that he reaches in again and takes another vanilla? Well, notice now there's 1 less vanilla donut in the box. So there's only 4 ways to get another vanilla, and since he took 1 out, there's only 11 donuts left in the box. So then what's the probability that he reaches in a 3rd time and gets another vanilla? You can see where this is going. There's only 3 now to choose from, and there's only 10 donuts left in the box. Right? And so if we were to multiply all this out and simplify it, we get a 1 out of 22 chance that Russell gets what he wants here and gets 3 vanillas. So that's just one approach, and this is one of my favorites. It's just list them out. Just lay out the options, multiply them together. Here's another way. We can use combinations. And this is not a bad way to go either. So how would this look in terms of combinations? So they basically explain it right here, but consider what goes on top and what goes on bottom. I'm going to kind of put this off to the side here where I have some room. All right, so whenever I lay out a fraction for probability, I like to start with the denominator, my sample space. How many total possible outcomes exist, right? So if I have a box of 12 donuts and I'm taking out 3 of them, my total possible sample space would be that there's 12 donuts, and I'm going to choose 3 out of those 12. Right? That represents the possible combinations of 3 I could get amongst these 12 donuts. So that's my sample space. Well, what goes on top? What goes on top is number of ways of getting what you want. Right? We want 3 vanillas, and how many do we actually have to choose from? Right? So this is where you got to get specific on this and say, okay, I want 3 vanillas. There's only 5 vanillas to choose from, so how many different groups of 3 can I get from those 5 vanilla donuts, or whatever these things are? So there's 5 to choose from, and we're choosing 3 of those 5 vanillas. Right? And so you could certainly set it up this way as well. This would also produce the same result, just a different approach. And this is not a bad way to go too, but sometimes using combinations can be a little tough for some. So it's kind of a fallback method. And that's what this is talking about, is you basically list out your options and multiply them together, which is what I did first. So, and that's what this multiplication principle of probability is saying. Just multiply the options together and see what you get. Okay. One of the things I wanted you to notice about the way that I wrote this out first is the numbers kept decreasing, right? It started out with 5 out of 12. I keep calling these donuts. I don't know if these are donuts. They keep saying chocolates, but whatever. It doesn't matter. Notice how the numbers went down. In other words, whatever happened on the first pick definitely affects what happens on your next pick, right? So whether I pull out chocolate or vanilla on this one has a huge impact on the setup that I would use for my second pick. So what we would call these are dependent events, because whatever happens here completely depends on what happens here. So these are dependent events. So that leads us into our next item of discussion, which are independent events. So how do independent events work? Well, independent events are events that do not affect each other. So a real simple example here. What if I said, I'm going to toss a coin and then roll a die? Right, I'm going to toss the coin and roll a die. Well, if I toss the coin, whether I get heads or tails, does that have any impact on the outcome of the die that I roll? Of course not, right? So those would be independent events because they have no impact on each other at all. Right? You'd simply look at the two separately, multiply them together. And the order wouldn't even matter in which you did those. It's funny because when you start getting into this, naturally, I start thinking of how people approach gambling, and the superstition that goes into gambling and betting and things like that. And if you were to, I'll give you a real simple example. If I were to toss a coin 10 times, and all 10 times it came up heads, and I said, okay, well then what's the probability of getting heads on my 11th roll or 11th flip? It's still 1 out of 2. Right? It doesn't change just because I got 10 heads in a row. I'm just as equally likely to get heads or tails on my 11th flip. It's because they are independent events. It's not impacted by what has already happened. And you see so many people, if they saw a coin flip 10 times and it came up heads every time, what do you think they're going to bet on? For the 11th flip, they're going to bet on heads because they're superstitious, right? But that doesn't exist. There's no such thing as luck. These independent outcomes are not affected by what's already happened. So I've been at blackjack tables at a casino or a craps table where you see people say, oh, you don't want to play here. This table's cold, or this table's hot. You should definitely come here and play at this table. It's total superstition that has no impact on what's going to happen next. But that's the way some people operate. So anyway, I wanted to introduce this formula to you. Here's the main way that we would view this formula. This is an interesting formula. The way we would read it is what is the probability of event B happening given that A happens? So what's the probability of event B happening given that A happens? Well, if these are independent events, it doesn't matter what happens on A, right? It's not going to affect event B. So the probability of event B given event A happens is still the probability of B, because A has no impact on B, right? And we're actually going to be using this in part 2 of this lesson when we talk about conditional probabilities, right? So they're giving us this condition of event A happening, but if these events are independent, then it's irrelevant, right? The probability of B is still the probability of B, no matter what happens with event A, if they're independent. So here's the formula that we would typically use, right? We're just multiplying the two events together. So the simple example that I just gave you of, flipping a coin and rolling a die, well, I would just look at the two probabilities separate and I would multiply them together. Let's go down to this one. Give you one of their examples here. Okay, so according to American Red Cross, distribution of blood types in the U.S. are such as follows. So you got type O, type A, type B, and type AB. So two people are chosen at random. What's the probability that they both have type O blood types? Well, look at these for just a minute and let's determine, are these independent events or are they dependent? Well, if I were to look at two people, if the first person I get has type O, does that have any impact on the second person I get? Definitely not, right? Because it's 45% that a person is type O, and that's not going to be affected by somebody else that I looked at. If it's 45% likely to happen, then it's 45% likely to happen on each one separately, right? And so just to look at the two, we would say, well, there's a 45% chance that the first person is type O, and a 45% chance that the second person has type O. So we would just multiply those together to get our results. The probability did not change no matter what this one is. They're independent events. So what's the probability that neither have type A? Again, independent events, let's just multiply them together. This brings up another formula. And just think logically about this one. This is called a complement event. If we wanted to say that neither has type A, well, here's the best approach for this. If there's 11% that it's type A, what percent is it that it's not type A? Well, it'd have to be the remaining 89%, right? It's got to add to 100. So in this case, I would just say, well, what's the probability that neither is type A? We would just say, well, it's 89% for the first one. It's 89% for the second one. And we would just multiply those together. So probability that both have the same blood type. So this is where you'd have to start looking at multiple combinations of multiple blood types, right? So if we wanted to lay out the cases where they both have the same, we would say, okay, I have to now look at all the possible combinations where they are the same. So it could be both type A. So we would multiply those together, or we always add these options together. They could both be type O. We'd have to look at that as an option, or they could both be B, or they could both be AB, right? So there was 4 different types of blood, and so we would have to kind of list them out separately and multiply them together. So you'd have 4 different layouts that looked like this. All right, let's talk about Venn diagrams here. So this is the last thing we're going to talk about in this lesson. I know you guys have seen Venn diagrams before. I just wanted to talk quickly first about the different areas of a Venn diagram. And then we'll get into a specific example. So real quick, each circle represents a different event, right? And so we're going to call this event A, and we're going to call this event B. So two different events. What do we see right here in the middle? Right. Well, this is what they have in common. This is the overlap. Right. So this area represents the outcomes of both of them happening. Right. So this would be all the probability or sample space of both events happening. So what about this guy? So this would be the percent that event A does happen and event B does not happen. So let me throw in some symbols for you that you might have seen before. This is what we would call A and B. All right, that's A and B happening. This would be the area that event A does happen and event B does not happen. Would be that area right there. So this is a very specific group, right? It's all the cases where A does take place, but we also have to consider this has to be cases where B does not take place, right? Otherwise it would have fallen into this category. So a similar idea over here. This is the cases where event A does not happen and event B does happen. If you were to look at all three of those areas, right? So if I really wanted to talk about all of A or B happening, all three of those cases, everything inside those two circles are what we would call A or B, right? Looks like this. All right, that's what we would call A or B. So this idea represents all of these probabilities being added together is A or B. So what does that leave us with out here? This would be everything that would exist if A or B does not happen. So usually the way we would identify this is we would say this is everything that is not A or B. All right, so if these circles represent A or B, this is the complement to that. This is everything that is not A or B. One thing that should take place in terms of probabilities is that plus that plus that plus that should add up to 100%, right? Because this rectangle represents the total sample space that could exist within a probability. So those four items should add to 100%. Let's take a look at how we could put this to use. Guys, notice with what I just drew, there was two circles, so that would be the layout for two events, right? If you had three events, you would need three circles, right? And so that we're just talking about two events right now. So in this one, we got 54% of students that are girls, 62% of students play sports. Half the girls at the school play sports. So this one was a little tricky because the percent that they give us in the problem is about girls, but the questions they ask are about boys. So let's identify within the question, what are the two events that we're talking about? We're talking about sports and we're talking about the boys at the school. Okay, and so those are the two percentages we're going to need to know. So if we were to set up a diagram for that, our two events are the boys and the sports. All right, and that's what these two circles need to represent. So I'm going to call this one boys and we'll call this one sports. Whenever you fill out a Venn diagram, you always want to start with the middle. All right, you want to start with the middle. So as I look at this, if I were to actually fill out a diagram, I need to know what is the percent of boys who play sports. Sorry, there we go. So because this problem doesn't tell us that, that's actually what we're solving for. We actually would need a formula for this instead of the Venn diagram. So I'm actually going to go a little out of order right now, and I want to show you a traditional Venn diagram problem before we actually start using the formula, and then I'm going to put it all together at the end here. So just look at this example 7 for a sec. So this one is a candidate for going directly into the Venn diagram because it tells us the middle section. Okay, so it's talking about 68% of students have a cell phone, 77% have an iPod, 62% have both. And that's our key, right? This is the middle of that Venn diagram. So let me do this kind of off to the side here. So this is our cell phone, this is our iPod here. Okay, so again, we always want to start with the middle section when we're filling out a Venn diagram. Okay, so if 62% have both, then I want to start with that right there. Okay, so here's the key, and if anyone messes this up, this is usually where it happens, so pay close attention to this. 68% of students have a cell phone. This entire circle represents the cell phone people. Okay, so that means this entire circle needs to represent 68%. Well, we have already put in 62%. So how much are we left with for the cell phone only crowd? Right? So again, it needs to total 68%. So if we've already put in 62%, then I have a remaining 6% of students who are cell phone only. So remember what this represents. This is people who have a cell phone and do not have the iPod. Let's do the same thing on the other side. So 77% have the iPod. So again, this entire circle needs to represent those 77%. We've already accounted for 62%, so the remaining, and this is where you subtract, the remaining 15% are iPod only. So remember how we would interpret that. So we're going to say 15% of the students have an iPod and do not have a cell phone. Right? This is who has both. This is who has cell phone but not iPod. Okay, so we always want to interpret that because depending on what the question they ask, right, we want to be able to know what these numbers represent. Let's just finish one more idea here. So if I were to ask you this first question, how many have a cell phone or an iPod? Right, that or question is referring to all three of those groups. Right, all three of those are people that have either a cell phone or an iPod or both. Right, so if we just add those together, so we have our, what's that, 68 plus 15. So if we looked at, what's that, 83%? Oops. That tells me that 83% are in those circles right there. So for who has the cell phone or the iPod are those 83%. Right, and that was the answer to the first question they asked right here. So what then is out here? Right, if I just want to look at this outer space. So if you think about what I said on the diagram a couple minutes ago, if this represents 83% of people who have one or the other, then this area represents the remaining 17% who don't have anything at all. Right, those are the 17 that don't have a cell phone or an iPod, is how we would interpret that. So what percent have a cell phone or an iPod, but not both? But not both. So kind of a key phrase. So this is the 83 that have one or the other, but now they're saying, but not both. In other words, cell phone only or iPod only. Right? So I would add those two sections together, and those add up to 21%. So really important that we can interpret the four different sections of that Venn diagram. Okay, let me go back to the formula. You'll notice in the question we looked at a second ago, the one thing they're not telling us was that middle piece. Well, we need to know the middle piece in order to fill out the rest of it, because we have to subtract our way out to get those. And so as I look at this, if they don't tell me what the middle piece is, how do we get it? That's where this formula comes into play. Okay, so this is how you will figure out that middle piece. So if I know the two events, and I know the total for how many have one or the other, I can simply do a little basic algebra here to figure out the overlap. So let me take you down to this one, and then I'm going to go back to the previous one at the end, because it's a little tricky. That one was like kind of a harder level of question. Here's a little more of a traditional type of a problem for this. So notice this one says there's 40 students in a class. So this rectangle, this Venn diagram, contains all 40 students. 33 of them own a dog or a cat. 25 own a dog. And 20 own a cat. So obviously we're talking about dogs and cats here. So let's call this D and C for dogs or cats. So the one thing I would need to know in order to fill all this out is what's that middle piece? How many own both? How many own a dog and a cat? And they didn't tell us that. So this is where the formula is going to come into play. So on this one, it said 33 of them own a dog or a cat. Okay, and so if you look back to the formula, in fact, let me just do this. So we have it in front of us. So they said the probability of dog or cat should equal the probability of a dog plus probability of a cat minus the overlap of dog and cat. All right, so let's just plug in what they told us. So in this case, 33 of them, dog or cat. Probability that they own a dog, well, there's 25. Or a cat, 20 own a cat. So the first thing we're going to figure out here is, then what does that mean for the middle piece? How many own dog and cat? Right, and so if we do a little basic algebra on that to solve for x, what would that be? 45, difference is 12. Okay, and so there must have been 12 that owned both dog and cat. And recognize I'm just putting the straight number there. I did not actually create the probability yet. If you really wanted to write this as a probability, we would say 12 out of 40, since there was 40 students. And you could create a percent, but I'm going to hold off on the probability till the end, until we need that. So let's just subtract out and get our numbers here. So remember, it said that there was 25 that own a dog. Okay, so this circle needs to total 25 people. Okay, and we've already accounted for 12 of them. Right, these were dog owners. So the remaining 13 are dog only. So again, all 25 of those are dog owners. 12 also own a cat. 13 are dog only. So if we look at the cat people, there was 20 that own a cat. We've already identified 12 of those cat owners. So the remaining 8 are cat only people. So what does that leave us with for don't own either one? Right, so if we total, what would that be? 20 plus 13 is 33. So I guess we already knew that. So the total was 33. So if we subtract that from our 40 students, that means there are 7 in the group who don't own either one. Okay, and so now that we have this filled out, and all these would be divided by 40 if we wanted to convert them to a percent. So now let's look at the question. So what's the probability that a student in the class owns only one type of animal? So they could ask you all kinds of questions now. They could say, how many only own a cat? It would be 8 out of 40. How many own both? It would be 12 out of 40. How many don't own anything? 7 out of 40. And so you could really answer any question now from this diagram. So only one type of animal, right? You got the dog only and the cat only people. So the 13 plus 8 out of the 40 is going to give us that probability. So if we did 21 divided by 40, we would say about 52.5% would be the probability of randomly selecting one of those students and it being someone who only owns either just a dog or just a cat. Okay, well, let me finish this one off now by going back to sort of a tougher question here. This one was a little tough to work through. In fact, I might change this to girls in sports, for it to make a little more sense with the way they worded this question. But it was a little tricky, but let's go through it. All right, so I'm going to change that to girls. Let's just start filling out whatever information that we can with what we got. So 54% of students are girls. So this circle needs to total 54%. Half of the girls play sports. So the reason I changed this to girls is so that I could fill out this diagram. So if it said half the girls play sports, so that means half of the 54%. So that means 27% would be the girls who play sports. That means the other 27%, the other half of the girls, don't play sports. All right, is what we got right there. So how many play sports? It says 62% of the students play sports. So that means this needs to total 62%. Again, we've already accounted for 27%. So if we subtract that from 62, that'll tell us the sports-only people. So that means there is 35% of the students do sports only. Okay, so what does that leave us with for out here? So if we add those three numbers together, so if we did 54 plus 35, what does that give us? 89%. So if there's 89% within these categories, that means there's a remaining 11% out here that is neither one. So these 11% are people that are not girl or play sport. Okay, now let's peek at their questions. And this is where it got a little tricky, but we got good percentages to work with. So what percent of students who play sports are boys? So as we look at this, remember how we interpret what's in this category right here, right? Since this was girls and sports, and this set was girls, as we look at these are people who play sports and are not girls, right? So these are 35% of the students who are playing sports and are not girls. So the way they set this one up was to say, well, let's just consider the sample space here. Sample space of students who play sports, 62%. That's our sample space. That's the total that play sports. Of those 62%, what's the probability or what's the percent of boys that play sports? It would have to be that remaining 35%. Right? And so you would have to divide those numbers to get that solution. So tricky way that one was worded. A student's chosen at random, probability that's a boy who does not play sports. Well, as we look at the diagram, remember, these would have to be the boys who do not play sports. So it would just be 11%, right? Because everything else has been accounted for within those sections. So if it was a boy or played sports, it would have to be in these categories up here, right? So we already took out the girls and we're taking out the sports. So what's left would be boys who don't play sports. So that would just be 11%.